So please repeat please your question in the chat because time was over. Okay. So we were talking about how to find the velocities at different points from 0 to 12 seconds. So if we take an interval of 2 seconds, then the points where we will compute the velocities will be t equals 0, t equals 2, 4, 6, 8, 10, and we will just have to do calculation at 6 points. However, for example, if we decide to divide delta t by 2, then the number of points we will have to calculate will be multiplied by 2. And of course, let's say if you take t equals to 0.5, then you will have to compute your velocity at 24 points. Okay? So smaller is your delta t, larger will be the number of calculation you should perform, but you will be closer to your exact solution. Okay? So now let us compare what we get here, the numerical result we get, with the analytical function that we have. So this is our analytical function. This analytical function, we know its exact, yani this numerical equation, if you want, we know its exact analytical function. It's this one. So we can say that this is the numerical equation and this is the analytical equation. This is the exact solution, okay? And now we want to compare if the numerical solution is able to really be close to the exact solution. So to do this, we will plot this function, and this function is continuous because when you have the function, you can replace at any time t. It's a continuous variation. Okay. While when you do numerical methods, you just get points. This is the difference, the main difference. So the exact solution is continuous. However, the numerical solution is discrete. Okay, so this is the difference between continuous and discrete. But as delta t becomes smaller and smaller, then you will have a higher discrete points, and then you will be close to the exact curve. So let us see this. We will represent graphically the analytical and numerical solution. So as you can see, the blue curve is a continuous curve and it represents the exact solution of our equation. So we say it's a continuous, this is a continuous representation. So it represents the actual function. So continuous curve. So it represents the exact solution. While here, if we take delta t equal to 2, we are just able to draw 6 points. So 0, at 2, at 4, at 6, 8, 10, and 12. Already we have 7 points, but the first one is already given. So we just have done the calculation on 6 points. So we have 6 discrete points. As you can see, the approximation is acceptable. The error is relatively small. So our numerical technique is working well. Okay, but I have a little bit here, the numerical value is a little bit higher than the exact value, but it's fine, and the error is not very high. And now if I join the points, I can get a closed curve. So my curve will be close to the exact solution, but with a little difference. So we have a little difference between them. Now we will see that to reduce this difference, the strategy will be to increase the number of points. But of course, as we said, we will need more time for computation. So let us take now delta t equals 0.5. In this case, we will have to do calculations at 24 points. So the number of points compared to 2 is multiplied by 4 because delta t is over 4. So from 2 to 0.4, I divided by 4. So the number of points will be multiplied by 4. So number of points will go from 6 to 4. Okay. So 6 times 4, 24. So it will go from 6 to 24. It's multiplied by 4. So the computational time will also will be much higher. But look, the result is worse because now when I take this high number of points, I can really nearly I approximate the blue curve with a very good accuracy. And nearly the error is very, very small so that I can see that nearly they are coincident curves in this case. So this is a good result. So now I can say no need to go with smaller delta t because delta t equals 0.5 seconds was really good in assessing the exact and giving a value that is close to the exact value that is obtained analytically. Okay. Now, in any numerical method, okay, I can have here, for example, it was very good. I didn't face any problems. Just I say if I want to have a more accurate result, I should reduce delta t. It's very fine. It's very good. But relatively here, the function involved was simple. We will see after that with more complex equations, the solution might I can have several choices, and sometimes I can have divergence. So it will be critical to select the appropriate method and to avoid getting divergence. So for example, if you solve if you want to predict the air distribution resulting from an HVAC system, let's say, okay, you can draw it in a CFD software, computational fluid dynamics software. You just give inputs. So what is the velocity at the inlet? What is the temperature at the inlet? And how the air will be, how the flow distribution will be in the room. You can predict the flow distribution, the temperature distribution, etc. So you need to provide information about velocity boundary conditions, temperature boundary conditions. And sometimes you might have, when you solve, you will see the residuals. So what we mean by residuals, when you have an equation, when you write an equation equals to 0, the numerical solution will never give you 0, but you can approach 0. So you can have, as you do iterations, for example, you can have what we mean by residuals, it's the number after the equal sign. So instead of 0, you might have 10 minus 4, 10 minus 5. So you will choose, you will select a certain criteria to stop. So you will say, when I reach residuals of 10 minus 5, for example, I will stop iterations. And I will consider that my CFD model has performed the required calculation, and I can take the temperature and velocity. So what you will do, you will observe your residuals. You can, during a CFD simulation, you will see residuals, how they are decreasing. This is what you wish. You wish that residual decrease until reaching a certain criterion that you specified. For example, here 10 minus 5. So automatically, when it will reach 10 minus 5, it will stop because you will set that the criteria of convergence is to reach residuals equal to 10 minus 5. And you don't have just one residual because you know that in a fluid problem, you have to solve for the temperature equation, you have to solve the energy equation, which will give you temperatures. You need to solve for the velocity field through momentum equations, and etc. You have also, if you take a CFD course, you will see that you have equations for turbulence in case your flow is not laminar, etc. So it's a very wide field. So you will look at your curves that should converge. This is what you want. You expect to have this result. But sometimes when you observe your residuals, instead of converging, they will diverge. And they will go to non-defined values. When you reach, and then the computer will give you a warning message that you read none. It will give you this, none. This symbol means it's not a defined number. So then your solution has diverged. And you should try to, with your experience, you will know what should you do to avoid this. What numerical techniques you should use, what should be your grid size, what should be your time step in case it's a transient application, etc. So this course will introduce you to these numerical techniques and will help you into avoiding divergent results. So when we say numerical result will blow up, this means that they will diverge until reaching a non-defined number. So we can encounter this in real applications, and we want to try to avoid this and try to learn strategies to not reach such conditions. Another issue that is very important is to know what are the techniques that we can use to improve the accuracy of the numerical methods. So here, for example, just in this simple example, the method to improve the accuracy was to reduce the time step, and it worked very well in this problem. Another very important criteria is the computational time. Because sometimes you can say here, for example, I reduce delta t, I get a better result. So why to not reduce it a lot? I keep reducing delta t until reaching a very good fit with the curve. It's true that your accuracy is increasing, but also your computational time is increasing. And here we just give a small example, but in real case, if you want to simulate a building, if you are using CFD and you want to simulate a building, you will end up with millions of elements. So if you choose to reduce your grid size more, then you will end up with a very high number of elements, and your computational time can be very long. So, for example, if you take an office space, if you take more than 2 million elements, for example, it can take you 1 week to get the temperature and velocity field, which is not very acceptable. If you want solutions that are fast to be efficient at the end, your research time is very important. So you should select the appropriate parameters that will give you accurate results and will save for you the computational. Okay, so let me check your questions. Karen, the solution diverge for several reasons, because sometimes what will happen is that from iteration to another, okay, instead of getting closer to the solution, you will get values that diverge from the solution. You have several rules, and mainly numerical issues. For example, it can be due to the round of error. It can be, sometimes we will see together that even if you reduce a lot the time step, sometimes it can give you bad results, because whenever you let's say you reduce delta x or delta t, okay, it's what you are reducing is the truncation error that we will introduce in next chapter, but you are increasing the round of error. So sometimes when you do this, and the error is equal to the total error, so some strategies can reduce one type of error and increase the other type of error. So in total, you can have divergence. Okay, and you have several sources of divergence. It depends also on sometimes if you have coupling between the different variables, it becomes more complex. A very small divergence in one parameter will affect all others. So you have divergence is a very complex field, and it can have several causes. Okay, we will try to develop techniques to reduce the possibility of divergence. Okay. Okay, guys, so we are done for today. This is the introduction chapter. You already have on Blackboard the syllabus and the introduction chapter. Tomorrow, we will start with the first chapter on numerical methods that will deal with errors. What are the type of errors and how we can assess the error of in computing any number in a computer, in a calculator. So now you will learn in next chapter how computers and calculators work with numbers. It's a little bit maybe strange for you. You will see that they always work. So for a computer or for a calculator, they just work with 0 and 1. So they will convert from decimal system to binary system. And in this transformation, you have a certain error that will take place. So we will learn about these errors tomorrow, hopefully. Okay. Any question before we stop?
Doctor?
Yeah.
Doctor, I have a question. You mentioned something about the exact method is continuous and the numerical ones are discrete. Can you repeat this?
Yes, exactly. Yes, I will. Okay. Look, if I give you a function, okay, if I tell you, for example, an easiest example of fx equals to x, okay? So this is a straight line, and you can compute it at any x you want because you have the direct relation between fx and x. If I tell you, for example, fx equals 2x, you can now tell me I can give you the value of fx at any x position you want, okay? So, and you can draw it, if you want to draw it on your graph, it would be a straight line. You just need to know, for example, two of its points. Let's say 0, 0. And for x equal 2, you have y equal 4. So you draw your line. It's this line is infinity of points. So when you draw a curve, you are not just drawing just some points. It's a continuous curve. This means it includes infinity of points. Okay, and you are able to assess the value of fx at the exact value of fx at any point I want. So I can tell you directly at 6.5 what is fx. You just put 6.5 times, so it's 13. You just directly give me the value. This is why it's called a continuous function. Okay. While when you do numerical techniques, automatically you are just assessing the function at certain points. So for example, depending on your time step, okay, here, if I give it function of x, the variable is x. If you want to use numerical methods, you will use there's certain delta x, okay? So for example, you will compute at x equals 0, at x equal 2. If delta x is equal to 2, let's say, here, of course, the function is very simple. You will not need a numerical method to represent it. It's nothing. I'm giving you an example. Okay, so let's say you want to represent this function using a discrete method. You will take delta x equal to 2. So I just represent fx at 0, fx at 2, fx at 4. Okay, so I know just when you just know points of your function, then you say that it's a discrete representation. And when you have a numerical solution, you are not able you need approximation to compute any value in between, but you don't have directly a way to find what will be the value between the discrete points. Okay, this is why we say it's a discrete technique of representation. So if you go back to the example here, when you take delta t equals to 2, okay, if I tell you what is the velocity at 1 second, you say I will do an approximation to tell you. But you cannot give me a number, an exact number, without doing the approximation. While if I give you the analytical solution here, you just replace in your analytical solution, all you have to do is to put at T1 in this equation and get V. So this equation will allow you to assess your velocity at any position you want, at any time you want. Okay. While for numerical techniques, you can it depends on delta t you selected. So you just know the value of your velocity at certain fixed points, at certain discrete points. And then if you want to predict any other value at any different time, you need to do an approximation. Okay. So this is a numerical solution. It's a discrete solution because it just gives the value of velocity at discrete points. While for the exact solution, it can give me the velocity at any point I want, and it will give me a continuous representation. Okay, guys, so I will pause.
Doctor, excuse me, how do we study like this case when we're gonna revise it?
Okay. When you want to revise, what you can do, the better thing to do is to practice and to repeat the calculation, to be familiar with the techniques. Okay. So first you can, for example, repeat this problem. You can try to develop the numerical method and to find this equation on your own. You find vi plus 1 function of vi. And then you practice with this example. If I take delta t equal to 2, you should make sure that you can get the same numerical values so that you understood well the technique. And then I will post an assignment for you on each chapter for practicing problem. And this course is really not hard because you are learning techniques and you should know how to apply them. You should just practice to be familiar with techniques and to be fast in your solution. Okay? So just if you repeat the problems we do, assignment I will post for you, you will be well prepared for the exam. Okay.
Doctor?
Yes.
Calculation errors are very possible in this course. How do you deal with them in the exam?
In my exams, I always tell you to write a draft and to take photos of the draft and send it by WhatsApp at the end of the exam. So I will correct mainly your draft. Okay, to take into account that you might have a calculation error. So what I care for is that you know well the techniques and you know how to apply them. Of course, as you said, for this course, the calculation is very important. So you should try to be accurate and try to be to do well, to avoid calculation errors. But if you, at the end, I will put partial grades. So in case your technique is right, just you did a small calculation error, it's fine. I will remove just a small number of points, but you will get 80% of the grade. Okay. Okay. So
Doctor,
yes.
I want to talk to you about registration فما بعرف إذا في هلا ولا at the end of the class.
I will stop recording and we will talk about it. Okay. Any other question on the introduction before we start? Okay. So see you tomorrow. Bye.